I believe this is the sixth video in this section, which is kind of absurd. I'm getting pretty tired of this material, and so I can only imagine how tired of this material you're getting. So I'm going to try to keep this video and, sorry to break it to you, the next one, because there's going to be two more, as short as I possibly can. We've learned how to take the derivative of a lot of stuff, but our end goal in this class is to be able to take the derivative of any function. What else could we possibly need? What kind of functions are out there that we don't know how to take the derivative of? Well, one class that we haven't learned yet are what are called exponential functions. So things like f of x equals 2 to the x power, for example. It's tempting to think that you could use the power rule on something like this, but you can't, because the power rule only works when your base is the variable and your exponent is a constant. Power rule works on x squared, not on 2 to the x power. Don't use power rule. Or maybe I should say you can't use the power rule on examples like this. So what can you do? Well, before I just give you the punchline, let me graph some things for you. In red here is f of x equals 2 to the x power. This exponential function kind of has this shape. When x equals 0, what comes out of this machine is 1. When x equals 1, what comes out is 2, because 2 to the first power is 2. When x equals 2, 4 comes out. I get this graph, exponential growth, maybe you've heard. If I went all the way back to our definition of the derivative, what that says is what the derivative is supposed to tell us is the slope of the tangent line to a curve at any given point. So if I pick a whole bunch of points on this graph, I could try my best to draw tangent lines. They're not great, but you kind of get the idea. What if we had to measure the slope of this line in purple right here? Well, it's definitely a positive number because it goes up when we read it from left to right. It looks like it's a little less than 1 to me, because a slope of 1 is the diagonal line that would connect this point, and this line looks a little shallower than 1. If I had to guess, I'd say the slope of this line is, I don't know, like 0.8 or something like that, something a little bit less than 1. What about this line right here? Well, this line is steeper than this line. It's definitely more than 0.8. In fact, if you look really carefully, I think it's even more than 1. It's going up quicker than our diagonal line would be. So if I had to guess this slope, I don't know, it's a little more than 1.4 or so maybe. But then the further you go to the right, the steeper these tangent lines get. What's the steepness of this graph? If I told you it was like 2.8, would you believe that? And you're like, yeah, sure, that looks like about 2.8. I don't know for sure. Well, look what happens when I plot those different points. A point a little bit less than 1, representing the steepness of this graph, maybe like 0.8 or so. A value a little bit more than 1, like 1.4 or so, representing the steepness of this line. And a value much larger representing the steepness of this line, maybe 2.8 or so. If I plotted the slopes of the tangent lines to this curve at a bunch of different points, what you'd see is it would trace out this graph in blue. Using methods that we haven't learned yet, I can tell you that the derivative of the graph in red is the graph in blue. They look really similar, right? And this is for 2 to the x power. We can do the same thing with 3 to the x power. When we look at the derivative of 3 to the x power and we plot it and its derivative on the same axes, we see that they look remarkably similar. The derivative graph of 2 to the x is a little bit less. It's this 2 to the x graph compressed down. The derivative of 3 to the x is a little bit more. Its graph is the same as this 3 to the x, but stretched vertically a little bit. How much is it stretched vertically by? It turns out that it's stretched vertically by the natural log of the base. What am I talking about? The derivative of 2 to the x power is almost just 2 to the x power. The graph in blue is almost the same as the graph in red. It's just compressed down a little bit. How do I compress a graph down? I multiply it by some constant less than 1. What's the constant? It turns out to be the natural log of 2. If you grab a calculator and you calculate the natural log of 2, what you'll see is it's some value a little bit less than 1, roughly 0.8 or so. So what I'm doing is I'm taking the graph in red and I'm multiplying each of the heights by roughly 0.8 to come up with the graph in blue. More precisely, the derivative of 2 to the x power is 2 to the x times the natural log of 2. And because the natural log of 3, if you pull out a calculator, is a number slightly more than 1, when I take the graph of 3 to the x, pictured in red, and multiply it by the natural log of 3, it gets stretched vertically a tiny little bit. Natural log of 3 is like 1.0 something, producing the graph in blue. What I'm saying is, without any proof, I would like you to believe me that the derivative of b to the x power, in other words, any exponential function, is almost just b to the x. You just have to multiply by the natural log of b. A cool little corollary of this result is, maybe you remember from several math classes ago, that the natural log of e is defined to be 1. Because the natural log of anything is just asking you the question, what power do you got to raise e up to change it into that anything? So if I want to change the implied e down here into an e, I have to raise that implied e to the first power, because e to the first power is equal to e. The natural log of e is just equal to 1. What that means is if I was taking the derivative of e to the x power, using this rule right here, I would say it's almost just e to the x power. I just have to remember to multiply by the natural log of e. That's what this formula right here says. But the natural log of e is just 1. So really my derivative is just e to the x power times 1. E to the x power times 1 is just e to the x. A cool thing about e to the x, and a way some people define e to the x, is its derivative is just e to the x. That's a really cool result, which will be useful later in our class. It's saying that if you plot the function and you plot its derivative, you get the exact same graph. It's saying that if you want to know how steep this graph is at any point, at this point right here, for example, how steep is the tangent line to this curve? All you got to do is figure out how high up the graph is. Another way of saying that is the rate of change of this function is equal to the value of this function. And that property ends up making e to the x really useful in a calculus class. But for our purposes, for now, just know the derivative of e to the x is just equal to e to the x, and the derivative of, I don't know, 5 to the x power? That's almost just 5 to the x power. I have to remember to multiply it by the natural log of 5. To see if that made sense, let me give you an example to do. Could you evaluate these two expressions? Don't forget the rules that you've already learned, right? This first one is 3 times the derivative of e to the x power plus the derivative of 1. I'm using my derivative sum rule and my constant multiple rule here. I got 3 times the derivative of e to the x, which is just e to the x, plus the derivative of 1. 1's a constant, so it's 0. I got 3 e to the x plus 0, or just 3 e to the x. Similar steps allow me to figure out this derivative. It's the derivative of 2 minus the derivative of 5 to the x power. The derivative of 2 is just 0, so I get 0 minus the derivative of 5 to the x power. As we talked about up here, the derivative of 5 to the x is 5 to the x times the natural log of 5. So my final answer would be negative 5 to the x times the natural log of 5. That's how you take the derivative of exponential functions. When you learned about exponential functions, I bet you immediately learned about logarithmic functions right afterwards, because those two are very closely related. Turns out that just like the functions are closely related, their derivatives are very closely related. I won't prove it to you, but you could take a look at the graph of the log base 2 of x and plot a bunch of tangent lines and consider the slopes of those tangent lines, and you'd come up with this graph pictured in orange as its derivative. If you know what the graph of 1 over x looks like, you might recognize that the graph given in orange looks a lot like the graph of 1 over x, but it's not quite 1 over x. It's 1 over x times some constant. And much like up here, that constant is dependent on natural logs. If someone asks you to take the derivative of the log base 2 of x, the graph that's pictured in purple, all you have to remember is almost 1 over x. You just have to remember to multiply that x by some constant. The constant is always the natural log of the base, 2 in this case. So what you see pictured in orange here is the graph of 1 over x times the natural log of 2. The rule for logarithms and the rule for exponential functions are very similar, but they're not quite the same. In this one, we multiply the top by the natural log of the base, and then down here, we multiply the bottom by the natural log of the base. It's easy to confuse those things, so be careful there. Another comment that I want to make. Remember that the natural log of e is just equal to 1. So if I was taking the derivative of the log base e of x, which is something you would never see written because people don't write the log base e, they write the natural log of x. What I would do using this formula right here is I'd say it's 1 divided by x times the natural log of e. Right? The natural log of x is the log base e of x, so playing the role of b in this formula is e. So I have 1 over x times the natural log of e, but the natural log of e is just 1. So this is 1 over x times 1, in other words, just 1 over x. A cool kind of useful result is that because the derivative of log base b of x is 1 over x times the natural log of b, the derivative of the natural log of x is 1 divided by x times the natural log of e, which is just 1 over x. Here's those graphs if you're curious. Let me give you an example problem, and then we'll end this video, although that means there's going to be 2 more videos in this section. Will it ever end? What if you're asked to evaluate this log? Again, don't forget stuff you've already learned. This is 3 times the derivative of the log base 2 of x. I'll figure out what that is in the next step, minus 5 times the derivative of the natural log of x, plus the derivative of the log of 100. 2 comments here. When you don't see a base written, implied is that the base is 10. So this is really the log base 10 of 100. Although it'll turn out that that doesn't matter at all. Why? Because this is a constant. You don't see the letter x anywhere in here. The log base 10 of 100 is just a number. It turns out to be the number 2, but it doesn't matter what number it is. The point is this is a constant, and the derivative of any constant is just equal to 0, so I don't even care what the base was here. When I take the derivative of this thing, I'm just going to put a 0 in right there. What about the rest of the terms? I got 3 times 1 divided by x times the natural log of 2 for the derivative of log base 2 of x, minus 5 times 1 divided by x times the natural log of e, or just x, for the derivative of the natural log of x, plus this 0 for the derivative of a constant. If you're the type that likes to clean up your answers, you might write this as 3 divided by x times the natural log of 2, minus 5 divided by x, and call that good enough. Speaking of calling things good enough, I'm going to call this video good enough and save trig functions for the next video.